Welcome friends. Today we would like to learn about the curvature and the radius of curvature. So this particular topic is very important if you would like to understand about the bending of the lines or bending of the curves. So let me begin with a simple example of a curve where we would like to understand the concept of curvature and the radius of curvature. So friends, if you see this particular curve, it has a different profile. You can see here, if you move along this particular curve from point A to point B, so you can see that it appears to be a straight line. So we are moving along a straight line. That means there is no change of direction when we move from point A to point B. But as we move further from point B along the curve, we see that we are consistently changing our direction. So this change of direction depends on the extent of bending of the curve. If the bending of the curve is higher, it means we have to change our direction suddenly. Let me consider few more points on the curve and try to understand the significance of the bending of the curve. So if we move from point B to point C, let's say, so there will be change of direction. So to find the change of direction, we can use the concept of tangent. So this tangent at point B, which I have drawn over here, this represents the direction at point B. We can draw a tangent at point C. So this is the tangent at point C. So the change of direction will be given by the angle between the tangent at point B and tangent at point C. So this theta BC, what I have shown here, that represents the change of direction when we move from point B to point C. Similarly, we can consider another point somewhere here at point D. So now again I have drawn a tangent at point D here, you can see. Now the change of direction while moving from point C to point D will be given by this angle, and that can be called as theta CD. The same procedure can be followed. So it means as we move along the curve, there is change of direction. So this change of direction signifies the bending of the curve. If there is sudden bending of the curve, there will be sudden change of direction. Let me take point E over here and point F at this particular point. Now this represents the tangent at point E, while this particular line represents the tangent at point F. Now you can see here, when we move along the curve from point E to point F, there is a 180 degree change of direction. So the angle between these two tangents are 180 degree, you can see here. So it means there is sharp change of the direction. Let me take one more point here. So this is F, and let me take this particular point as G. We have drawn a tangent at point G also, you can see here. Now this tangent represents the direction at point G, while this particular tangent represents the direction at point F. So when we move along this curve from point F to G, this is going to be the change of direction. So theta FG represents the change of direction of the curve from point F to point G. So we have understood how to find the change of direction, but there is a very important point to be noted here. Like when we move from point E to F, there is a 180 degree variation of the angle. The direction changes by 180 degree, while from here to here, the direction changes by less than 180 degree. You can see here. This angle is not 180 degree, while this angle is 180 degree between these two tangents. So there is sudden change of direction from point E to F, while there is a gradual change of direction from point F to G. So whenever there is sudden change taking place, so that is called as higher curvature. So this portion of curve has got higher curvature. So the curvature term indicates the variation of direction. While here, if you see, this portion of the curve has got lower curvature. This portion has got lower curvature. So variation of direction is gradual over here, you can see along the length of the curve. So this is having lower curvature. So I hope you have understood the significance of change of direction. If there is change of direction is sudden, then curvature is high, and if change of direction is gradual, the curvature is low. So let us define mathematically the quantity called as curvature. So the curvature is shown by a capital letter K, and it is defined at a given point of the curve, because when we move along the curve from point to point, there is a possibility that the curvature may change. So we define curvature at a given point of the curve. So the curvature K at any point of the curve is defined as the rate of change of direction of the curve with respect to its length. For example, as we move along the curve, how much change of direction is taking place at particular point? That change of the direction with respect to the length of the curve at a given point is called as the curvature of the curve. So friends, to understand the concept of the curvature, let's take an example of a circle. So considering a given circle over here, so we would like to find out the curvature of the circle. Considering a point A over here on the circle, and this is the center of the circle. Now the direction of the curve of the circle is given by this tangent. So this tangent represents the direction at point A. Considering another point on the circle as B. So this is the point B on the circle. So now when you move from point A to point B, so there will be change of direction. So direction at point A is given by this tangent, while direction at point B is given by this tangent, we can say. So the change of direction is given by this angle. Let me call this angle as delta theta. So change of direction when we move from point A to B on the circle. Now by geometry it is very much clear that if this angle is delta theta, at the center also the same angle has been covered by the radius delta theta. So the radius will also describe the same angle. So let's say radius r, the radius r is going to describe same angle delta theta at the center, right? So this delta theta represents the change in the direction of the curve from point A to point B. So we can write down that if you consider the curve AB, the length of the curve AB is delta s. So that we can write down here. So we have got the change of direction as well as the length of the curve between point A and B. Now as far as definition is concerned, so let's go back and see the definition. So definition says the rate of change of direction of the curve with respect to its length. So if you want to find out the curvature at any point of the given curve, we have to find the rate of change of direction of the curve with respect to its length. So here if I want to find the curvature of circle at point A, because the curvature is defined at particular point, so we can say that the curvature K at point A is the rate of change of direction. So the rate of change of direction is given by d theta, because theta represents how much direction is changed, and with respect to the length of the curve, that is ds. So where s represents the length of the curve. So this particular quantity mathematically represents the rate of change of the direction of the curve with respect to the length of the curve. So this is we are finding out at point A. So this is only possible if we reduce the length of the curve to a very small value. So point A and point B should be overlapping, should be very close, such that so we can find out the curvature at point A. So here you can see that this can be achieved by using limits. So if you apply limit delta s tends to 0, delta theta by delta s, this particular quantity will provide us the value of the instantaneous rate of change of direction with respect to the length of the curve corresponding to point A. This is what we can say the curvature at point A, right? Now for the circle, this particular rate is going to be constant because it's a uniform curvature. Circle is having uniform curvature. The bending is uniform throughout the circle, so it is having uniform curvature, uniform K. K stands for curvature. So I can also write down here, for circle the curvature is nothing but theta by s, because it is varying uniformly with s. But this will not be applicable for all the curve. It is only applicable for the uniform curve such as circle. Now from here we can get one very important output. So if you consider a sector OAB, so we can write down that delta theta as delta s, that is length of arc or length of curve, divided by r, the radius, because the radius is uniform throughout. So we can say delta theta equal to delta s by r. So we can also write down from here that r is delta s upon delta theta. So this is applicable when you have same radius throughout. But if you wanted to find out radius at particular point A, if there is a variation of the radius and you want to find radius at particular point A, so we can extend this concept, that is radius of curvature at any particular point A. So in that case you have to bring the point B very close to point A. So in that case delta s has to be very small. So when delta s is very small, definitely the delta theta is also going to be very small. We can write down this as radius of curvature at point A is delta s divided by delta theta, and provided delta theta is very small, that is tends to 0. So this quantity will become ds divided by d theta mathematically. So friend, this particular expression is called as radius of curvature at a given point. So we can also define the radius of curvature like we have defined the curvature for the given curve. So we can also define the radius of curvature. So the radius of curvature at any point of the curve is defined as the rate of change of length, that is ds, with respect to change in direction of the curve. So it is totally opposite to that of curvature of the curve. So the curvature of the curve is nothing but, you can see here, it is the rate of change of direction with respect to the length. But here it will be what? The radius of curvature is the rate of change of length of the curve with respect to the direction of the curve, right? So from this expression we can say from equation 1 and from equation 2 we can easily conclude that the curvature at a given point A is the reciprocal of radius of curvature at a given point A, right? So you can easily get this particular conclusion from equation 1 and 2. So kindly remember these three expressions. So this is curvature at any particular point. So we have used circle to define the curvature. So we got the expression for curvature at particular point on the curve. Okay, for circle it is specially theta by s because the circle has uniform curvature. Okay, so from there we got the concept of radius of curvature also, and we got that the radius of curvature is reciprocal of curvature. So this concept is applicable for any kind of curve. So now we would like to find out the expression of curvature and the radius of curvature of given curve. Let's consider a curve y equal to f of x in a Cartesian coordinate system. We have got an irregular curve, so whose curvature is varying. You can see that at this particular end the curvature is bending sharply, while this particular end has got less variation, again it varies. So this is a non-uniform curve, and we would like to find out the curvature and the radius of curvature of this particular curve at a given particular point. So we would consider the same concept here also. We shall be considering 2 points over the curve. So we have considered 2 points here. So one point, let me call this point as point A. Consider another point here. I am going to call this point as point B. So I have drawn tangent to the curve at this particular point A. So this indicates the direction of the curve at this particular point. So I have also drawn a normal at the same point on the curve, which is this. I have also drawn a tangent and the normal at point B on the curve. In this case the tangent also represents the direction of the curve. Now let us say both the normals are intersecting at point O here. I cannot call this O as a center because it is not a circle. So but the normal drawn at point A and point B are intersecting at point O. So let's say, so this tangent makes some angle theta with x-axis, and tangent at point B makes angle theta plus some change in theta, we can say delta theta with x-axis here, you can see here. So by geometry we can easily show that at the point O the angle will be delta theta, which is the angle between two tangents drawn at points A and point B respectively, as I have shown over here. Now we are interested about this part of this portion of the curve, which is AB. So if you consider the portion of the curve AB is having length delta s, a small length delta s. So if you move along the curve, there will be variation in the x coordinate, we can say it is delta x, and also there will be variation in the y coordinate, so that is delta y. So this seems to be like a triangle, a small triangle having delta as a small portion of the curve, you can see here. So now I have considered this particular portion of the curve. So this particular point is point A, and the coordinate of point A is x comma y, and this particular point, which is the second end of the curve, is point B, and which is having coordinate x plus delta x and y plus delta y, as you can easily understand from geometry. Now this angle, which is angle over here, can be approximately taken as theta, which is the tangent drawn at point A. So here angle made by tangent with the x-axis is theta. So let me call this point is point A, this point is point B, and let me call this point is point C. So if I consider triangle ABC, this is the curve, but since delta x, delta y and delta s are very small, you can approximate this portion as a triangle, right angle triangle. Here it is 90 degree. So approximately I can write down here as delta s square equals delta x square plus delta y square. you'll get from here delta s over delta x the whole square will be equal to, this will become 1 because we are dividing both sides by delta x square, so this will become 1 plus delta y over delta x the whole square. If you make delta x to be very small, so taking limit delta x tends to 0, because we are assuming that the portion of the curve is very small, because we are interested to find out the variation at point A. So I am taking delta x to be very small, that is delta x tends to be 0. So that will be simplified as limit delta x tends to 0, delta s by delta x the whole square equals to 1 plus limit delta x tends to 0, delta y by delta x tends to 2. So this will be definitely a quite simple term, and you all are aware of this. So by basic definition of derivatives, we know that this value is nothing but ds by dx the whole square, and this is nothing but dy by dx the whole square. So you can simplify this. So we will be getting a simplified expression as ds by dx would be equal to square root of 1 plus dy by dx. So this is a very important point. We can note it down over here. So let me call this particular equation as equation 1. Now we know that the slope of tangent to the curve at particular point is nothing but the differentiation or derivatives at that particular point. So we can write down like this, that tan theta, that is slope of tangent at point A, nothing but dy over dx, that is differentiation with respect to x at point A. So we are referring all the quantities we are referring at point A. That is simply I can write down dy by dx, because we are only referring point A, we are not referring any other point. So it is simply dy by dx. So we got tan theta as dy by dx, so we can also write down that theta as tan inverse of dy by dx. So this is the next equation we got. So let me call this as equation 2. Now we shall come back to the definition of curvature. So we would like to find the curvature at point A. So the curvature at particular point A is nothing but, by the definition, the curvature k at any point of the given curve is defined as the rate of change of direction of the curve with respect to its length. So as we know that the rate of change of direction is nothing but the change of angle between 2 points we can take. So by definition of curvature, we can write down the curvature at point A of the curve given as ka equal to the rate of change of direction of the curve with respect to the length of the curve. So the ka is given as limit delta s tends to 0, delta theta change in direction by delta s, that is change in length. So we have considered this curve and we have found the change in direction is delta theta between point A and point B, and the change in length is delta s of the curve, here you can see, and we have made delta s very small so that we find out the change at particular point A. So we have taken delta s tends to 0. So this is what? So this is nothing but, friends, d theta by ds. Okay, so this already we know, there is no big deal, because already we have derived that the curvature at any point is nothing but d theta by ds at that particular point. So the same way we have extended the concept to the given curve. So now I need to find out d theta by ds at particular point A. We are referring at point A only, right? So let me simplify this. So this is nothing but, so I will not write A here because it is by default we are referring to point A only. Okay, so I can simply write down this as d theta by ds, the rate of change of direction with respect to the length of the curve. Now to simplify this, what I shall do is, because I cannot directly find out the differentiation of theta with respect to length of the curve, so I'll do small modification, d theta by dx times dx by ds. So this will be a simple modification. We have used the property of differentiation, so we can easily find out d theta by dx in one part and dx by ds in another part. So you can see here we have already calculated the value of theta as tan inverse of dy by dx. Okay, this dy by dx refers to the slope at point A. So we can write down instead of theta tan inverse of dy by dx. So let me substitute here. So I'll be getting this as d by dx of, now instead of theta, this theta, I'll be writing tan inverse of dy over dx, which is slope of tangent at point A. And the second we have got dx by ds. Okay, so this is nothing but 1 divided by ds by dx. Now if you look at this particular term, this already we have calculated in our previous steps. So you can see here we have already calculated ds by dx. Okay, that is square root of 1 plus dy by dx the whole square. So I can substitute the value of ds by dx from here into this equation. So now it will be simplified further. So you should be getting the curvature at point A. Now differentiation of tan inverse is 1 divided by 1 plus dy by dx the whole square, and we'll be using chain rule. So that is dy by dx of dy over dx. So this is the first part we have done up to here, and this value already we have calculated, which is nothing but 1 divided by, let me take it, what is it, square root of 1 plus dy by dx square. So I'll put that. So square root of 1 plus dy by dx the whole square. That's very simple now. So just we have to simplify this in order to get the final expression of curvature at a given point A. So if you look at here, this is going to be second derivative of y with respect to x. So that I'll write down as d square y over dx square. That is okay. And in the denominator part, if you see, we have got square root of 1 plus dy by dx the whole square and 1 plus dy by dx the whole square. So here power is 1 and here power is 1 by 2, we can say. So it is going to be collectively 1 dy by dx the whole square raised to 3 by 2. So the curvature at point A is given by this particular expression. Now we know that the curvature is reciprocal of radius of curvature. So if you wanted to find out at this particular point A what is the radius of curvature, so let's say radius of curvature is r at this particular point A, so RA. So we can also find out the radius of curvature as reciprocal of curvature at point A. So we can also find out here directly the radius of curvature, that is r at point A. That is nothing but 1 upon curvature at point A, and then you can accordingly write down the expression 1 plus dy by dx the whole square raised to 3 by 2 divided by second derivative of y with respect to x. So these are two expressions we have got, and these are very important expression. So the first expression is for curvature at point A for a given curve, and the second expression is the radius of curvature at point A for the same given curve. So by using these two expressions, you can find out the curvature and the radius of curvature of any given curve. So I hope you have understood the concept of curvature and the radius of curvature of given curve, and also you have got the procedure to find out the expression for curvature and radius of curvature. So we'll stop here. Thank you very much.